one. Yes, I'm by the names of Chikula Brian. I'm going to be your lecturer for this course unit, DC machines and batteries. That is for the DEE Diploma in Electrical and Electronics Engineering. That is academic year 2, semester 1. This is our very first lecture. Lecture 1. Lecture 1, what are we going to be covering in lecture 1? So lecture 1 is just going to be all about the introduction to DC machines. So we'll look at the batteries. We'll look at the batteries part a little bit later on in the course. So let's look at what DC machines are. DC machines are nothing but DC machines are those that use or operate with DC voltages, with direct current voltages, and with DC voltages and magnetism to do work. And this work has to be done efficiently. To do work efficiently. So typically DC machines are made of motors, DC motors, and DC generators. So DC machines are typically made of DC motors and DC generators. In the consequent lectures, way down the road, we'll be dissecting and specifically going deep into details of each of these machines. So essentially, they are machines that use DC voltages and magnetism to do work efficiently. So I can't give a more simpler definition than this. So why wouldn't I go for a very complicated definition? Because it does not get the point across. We have a machine, we have work to do, and efficiently. Mark the word efficiently. You have to do work efficiently. DC voltages and magnetism. So let's clear the board and look at each of these. What does that mean? Before we even dive into what a DC motor is and a DC generator is. Let's look at, we've seen that DC machines deal with DC voltages, though this DC is not the only voltage we deal with when we are discussing or handling DC machines. DC voltages are not the only voltages in the picture. We will see that when we get to generator, how the armature generates AC voltage and how the commutator converts that to DC. We will look at that. Though in general, we describe it with what comes out from the output of, if it was a DC generator, if it's a motor, we only focus on what gets it to run. You get the point. So at this point, guys, I don't expect anyone, for those who are part of my UICT class, the Uganda Institute of Information and Communications Technology, NAKAWA. So I don't expect you guys not to have heard of what a motor is. So I will not define what a motor is at the moment. So I will just keep on using the term with a huge assumption that you guys have ever heard of what a DC motor is. So I was explaining, so it does not matter whether somewhere the machine uses AC or generates AC. We only look at what makes it run. If it's a motor, if it's a generator, we only focus on what comes out at the output. So we've seen that DC machines operate with DC voltages. They operate around the principles of magnetism, right? So one other thing, these machines operate on a few principles of geometry. If we have magnetism, how is the magnetism oriented? How are we going to get motion? If it's a motor, how are we going to end up with motion? So if it's a generator, how is the motion present in the generator affecting parameters like the voltage and the current on the output? So geometry matters. So then some basic principles. Some basic principles of electricity. So let me try to break down each and every one of these. So let me start from the bottom. So what do I mean by basic principles of electricity? I mean basic things we already know at this point in the course, because we are year 2 guys, not year 1. So what do I mean by basic principles of electricity? Things like Ohm's law, not Ohm's laws, it is Ohm's law, that show the relationship between the voltage drop across a load and the current through it, or the resistance. Let me represent it with the resistance. The resistance, then the current. The resistance of the load and the current. So Ohm's law best describes what happens to the current flowing through a certain load of a certain resistance provided with a certain voltage. So that's not the only principle we know of. At this point, I know you guys have done circuit analysis. So we do have KVL, Kirchhoff's voltage law. So this one caters for the total voltage across a loop is equal to the algebraic sum of individual voltages in that loop. V3 up to the nth voltage drop. So what is the other one? So the other basic principle is Kirchhoff's current law. So this one takes care of the total current, IT, total current I've denoted with T, total voltage I've denoted with VT, So that total current is equal to the algebraic sum of individual currents at a node, at an electrical node. So for those who don't understand the terminologies, feel free to inbox me. Yeah. For those who are watching these lectures and you happen to be part of my diploma, electrical engineering class, please inbox me if you don't understand anything I utter or the terminology is too hard for you. Let me know, inbox me. So getting back to topic. So let's say we have I2, I3 up to the inth branch. Inth branch. So you sum up those algebraically. So that means direction matters, right? So yeah. So let me try to make a pictorial representation. Let's say this is the total I is equal to the currents. This could be going like that. This could be going like that. So this could be I1, I2, I3, I4. We will need this principle when we are talking about coils, field coil, armature, shunt, compound. I don't want to get ahead of myself right now. So long story short, we will need these principles. So how much current do we have entering a node that's going to branch between two coils, then combine at the end? So we'll need that. So let's say we have a series, let's say series wound machine. We'll have individual voltage drops at individual coil edges. So how best can I represent this pictorially? All right, let me try. Let's say we have a voltage source with a couple of loads. These could be inductive and partly resistive. So, like coils are. So this is V1, V2, those being the individual voltage drops. So if V total is that, you have to sum up V1 plus V2 is equal to Vt. So Ohm's law simply explains the relationship between the current I flowing through a certain resistive load R. Resistive, mark the word resistive. That means this is an ohmic load. So it obeys Ohm's law, right? So with a certain voltage drop across it. With a certain voltage drop across it, V. So, and there is that relation, that IV relationship or VI relationship. So we need to have this in mind if we are to deal with DC machines, because they are circuits. That means they must obey the basic principles of electricity or electrical engineering laws. So the other one is geometry. Geometry, let me give you an example. So since we are dealing with, so let me go backwards on my word a little bit. Let me go backwards on my word a little bit, and let me start with let me start with the magnetism part. Let me start with the magnetism part. Okay, the magnetism part tells us something, that DC machines must be operating around some kind of magnet. Some kind of magnet with the North Pole and South Pole. So regions where the orientation of a magnet, magnetic orientation changes. So let me even draw a second magnet around here, permanent magnet. Let me start this start off this with a permanent magnet. So we are going to get back to this. Let's get back to geometry. Okay. Geometry is all about the effects. What geometry brings about is the effects to the magnetic fields if oriented a certain way. Oriented a certain way with respect to each other. Like in this case, we know the basic laws of magnetism. We know that like poles of a magnet repel. And we know that unlike poles attract. We know that unlike poles attract. We get the point. So in this case, we're going to have attraction. So, and we have field lines. Let's say these two magnets are oriented like so, and they are close. So this is how field lines, resultant, mark the word resultant, we will get to that. So these are resultant field lines, or what we will later on discover that this is what we call flux, regions where the magnetic forces concentrate the most. So we represent them with lines. We call that magnetic flux. So these will just attract, right? Because this is the south, this is a south pole, this is a north pole. And we will see how does that now, how does this relate to that? Then how does it play out with DC machines? So how does that play out with the DC machines? So I'm cramming my board. That's my style, guys. I even told this my power electronics class. I don't know. Call it being disorganized. All right. So what do DC voltages have to do with any of this? Let me give you one scenario. This is not the only reality. So let's say we have a voltage source, an ideal voltage source that is pushing current through a resistive / inductive load. Let me have a switch. Let me be a decent engineer and have a switch. All right, this has a certain voltage VT, and we have our load. So when I close the switch S, right? When I close the switch S, we can all agree, or I don't know, for those who have ever had this experiment conducted in your physics classes, for those who took physics as a major subject like I did, we realize that current will start flowing through the conductor, the load and the conductor, right? Funny thing is, if you bring a compass, if you situate a compass close to the wire conducting current, whereby we've closed the switch S, it deflects its needle. If it was pointing in a certain direction, the moment you turn on the current, it deflects a little. And we know a compass only and only reacts to presence of magnetic fields. So guys, I'm going to be a little bit slower with this course unit, unlike the power electronics course unit. Of course, for it, it's a bit straightforward. These machines, all machines in general, this is the reason as to why many students deem them very hard to grasp and internalize the concept, simply because one of the reasons is that them as students, they try to rush through the content, and maybe sometimes the content deliverers. So they try to rush the content. So, and there are very many things at play. Very many things we are yet to introduce that are in play for us to just have one section of machines that is DC machines. There is the other half that is AC machines. So, I was explaining how a compass works. So, without any presence of an external magnetic field, it will appropriately align with the Earth's magnetic field. I give you an assignment, I urge you to go and make research on how a magnetic compass, aligns itself with the magnetic field of the Earth, because the Earth is also a huge magnet. So we will get into those details later on. So that means a compass brought close. Let me have this marker represent my compass. So when the switch is open, the compass, let's say, is pointing in that direction, right? So when I close the switch, a current flows, the compass deflects, I was saying. And we know a compass only reacts to presence of an external magnetic field, different from the one that exists already. So that simply means the flow of current somehow turned the wire into a magnet. The wire somehow turned into a magnet. And the moment we open the switch, the current flowing goes to 0 amps, so no current is flowing. When the switch is opened, the magnetic compass goes back to its previous orientation. That simply tells us a principle. So this is the effect of electricity on magnetism. So on magnets. So the magnetic effect of electricity. Actually, that's the right word. The magnetic effect of electricity. Let me write it here. The magnetic effect of electricity. Magnetic effect of electricity. It simply tells us, what does that tell us? A current carrying current carrying conductor produces a magnetic field around it So a current carrying conductor produces a magnetic field around it. So let me visualize it a little bit here. Let me take just the conductor and its cross section, right? So I'm trying to bring it to 3D view. Excuse my art. Let's say the current through the conductor is traveling in that direction. IT. Let me just denote it with IT. So it tells us a magnetic field develops around a current carrying conductor. So now we are seeing the relationship, a direct relationship between these voltages and currents. One leads to the other, voltage leads to current, so long as you have a load. So we are seeing the relationship between magnetism and electricity. So let's call this electromagnetism. That's what we call electromagnetism, the relationship between electricity and magnetism. These two fields of science were discovered decades apart, decades and decades apart. So, but the relationship between them was discovered years later. So, and practical applications came of it, very many. You're watching this video right now because somewhere a DC or an AC machine is running, which simply relies on the relationship or exploitation of the relationship between electricity and magnetism. So, getting back to the current carrying conductor. So let's say it's carrying current in that direction. So how do we get to determine the orientation of the magnetic field around it? Because the area around a material where magnetic field, magnetism is being experienced, we call that a magnetic field. So it's like as if we have a magnetic field developing around the conductor the moment current flows through it. So let's look at the orientation. All right, so there is something I'm to introduce at this very point. There is what we call the right hand grip rule. So using the right hand grip rule, it goes something like this. Make a fist, straighten up the thumb, right? Straighten up your thumb. So let the thumb face the direction of the flowing current. Flowing current, right? So the curling fingers, curling means something coiling itself around. So the curling fingers give away the direction or the orientation of the field lines. So that's interesting. So that means if this is my conductor, holding it like this with the thumb perfectly oriented with or in the same direction as the flowing current, it simply means my fingers are going to represent the direction of the field. So that means it's just going to point downwards, right? So going to curl like this. That means it goes around and over. Okay, round and over. Okay, like that, like so. Again, excuse my art. Okay, so up and down, up and down. So that's how it's going to be. So that's how it's going to be. So what was this lecture all about? Preparing the right mindset, telling us what is needed in play. All of these things are happening at the same time. And they matter, they make the difference. If we are to deal with DC machines, that is generators and motors. So I'm not going to be making very long lectures. They are going to be short lectures, but in a series format as we progress through the course unit. Because since we are watching this under the eCampus program, we are going to be under the eCampus program. We are going to be conducting these lectures online, pre-recorded lectures. So they are not fun to watch for 1 hour straight, 2 hours straight, but it's important since everyone is to watch at their own convenient time and place. So I decided I'm going to be making short videos, but with a good number of them on a single topic or subject matter. Thank you for being great learners and attentive learners. Let's meet in the next lecture where we are going to get back to what a DC machine is. Thank you.